Welcome back, everybody. The first thing I want to mention is that the extra credit is due on Friday. For you watching the video here, it's also due on Friday. Did I say you could just send it to me by email? Is that how I said to do it? Or you can either give it to me in paper form, or you can send it to me attached to an email. Either way, it's easy enough for me to grade it. You know, and I'm not going to grade it. I'm just going to look and see if you said something. And if you did something decent, you'll get the extra credit. I'm not going to sit here and assign points and do all that kind of thing. Not for something like that. And I don't want it to be a kiss-ass job either. Okay, I mean, I want it to be just what you thought. Okay, I want it to be honest. So that's due on Friday, folks. Also, there will be another video that I will put out tomorrow. It'll have to be a little bit later in the day because I have classes in the morning. But I'll try and get it out. Those two videos are replacing lab this week. The lab is due, the vector lab is due next week on Monday or Wednesday, depending on which group you're in. If things go well, I will have a torque lab available for us that I will be handing out next week on Monday and Tuesday because we should be getting to torque either today or tomorrow. As I mentioned, when I finish chapter 4, I'm going to jump to chapter 8 and talk a little bit about torque, and then jump to chapter 9 where we do statics. And the statics problems are really an extension of what we're doing right now, except the acceleration is zero. Free body diagrams, writing out Newton's equations, finding the equations, it's all exactly the same thing, except the acceleration is zero. And it's a very special class of problems. All right, now, first of all, I need to mention that I made a mistake. I noticed it looking quickly back at the video. And in the last video, I had this on the board, and this should not be here. The normal force is mg cosine theta. I was rushing there and dropped the negative sign. One thing that we're going to see in problems that we are doing is that usually in these equations, the quantities that we are solving for are the magnitudes of the forces involved. We're solving for the magnitude of the forces. Magnitudes are always positive. And if we solve a problem and get a negative value for a magnitude, that usually means that there's something set up wrong in the problem. It's an indication that something that we assumed at the start is wrong, or that we made a mistake. All right? If we had a negative sign there, that would indicate that a mistake was made. Well, I made it when I moved this to the other side. It was negative. It should have become plus. At the end of that problem, which is the skier moving down the incline. We assumed we had a skier here of some mass moving down the incline. The key idea here is using a tilted coordinate system. A tilted coordinate system greatly simplifies things. So we were using a coordinate system that was tilted like this, with x down the incline and y perpendicular to the incline. And I believe, I got to get it off the top of my head, that the other equation we had was that MA was equal to minus FK plus mg sine theta. This came from considering the y situation. This came from considering the x situation. However, now we'll start the new stuff. Once you know the normal force, you automatically, if you are given the coefficient of friction, you automatically calculate the frictional force. So we know, I think we were also given that, what was mu sub k, 0.1? I think mu sub k was 0.1 in this problem. This was a skier, yes, that's reasonable. So once we get this, we can automatically calculate the frictional force. However, we're doing this algebraically, and this is a problem that must be done algebraically for us to see what happens. This is mu sub k, and then we put this in. Fn is, Fn, since we're doing that, is mg cosine theta. mg cosine theta. Now, what should I do with this? I put it in here. So what I get when I do that, ma is equal to minus mu sub k mg cosine theta plus mg sine theta. And at this point, who sees it? What happens? What does every term in this equation contain? Ma is minus mu sub k mg cosine theta plus mg sine theta. What does every term contain? M. If I multiply both sides by 1 over m, or equivalently if I divide both sides by m, the m's all cancel out. They have to all be the same m. And we get that the acceleration, and I don't like to have leading negative signs, is g sine theta minus mu sub k g cosine theta. And there is the answer for the acceleration of the skier. It does not depend on how heavy the skier is. What essentially happens is, if we have a bigger skier, the coefficient or the component of gravity down the incline increases, the normal force increases, the frictional force increases, and it is such that the m cancels out and the acceleration is independent of the mass of the object, which is amazing. This often happens with gravity. This often happens, often happens with gravity, but not in every single case when we have something sliding. But it happens when gravity occurs. But you don't assume it happens, you prove it happens. You prove it happens. The only way you can go forward is at the start of the problem, make an assumption that it doesn't depend on the mass, proceed forward, and in this case, indeed, it did cancel out. And at this point, you put in 9.8 meters per second squared. Theta was given as 30 degrees. Again, you should calculate this. They do this in the text. And what actually happens here, you can write this a little bit more fancy. What does each of these terms contain? A g. So you could factor out the g. And you get that the acceleration is g times the sine of theta minus mu sub k cosine of theta. And so when you put this all in, that actually evaluates to 0.41. And so what happens is the acceleration is 0.41 times the acceleration due to gravity. Oftentimes, accelerations are given in terms of multiples of the acceleration due to gravity. You could put 9.8 meters per second squared in there and get a number if you wanted. It's about 40% of what would happen if she jumped off and went straight down. That's how you look at that. If the skier just jumped off a cliff and was in free fall, her acceleration would be g downwards. Here it's about 41% of that, going down a 30-degree hill in this case. Now I want to do my own problem. So get your calculators, because right buried in here is the solution to another problem. Does anybody have any questions? There's no such thing as a dumb question. There's no such thing. Okay, now, in one of our labs, we had an air track, right? And we let the air track slide down the incline. No friction now. Air track, no friction. This was our recreating Galileo's motion experiments lab. And the situation here was exactly the same. Here's our air track, but no friction. Which means that mu sub k is 0. And when I released the glider and when I timed it, I think what I got was 2.15 centimeters per second squared. Does that sound right? Yeah. We found that the acceleration was 2.15 centimeters per second squared. Now remember that g is 981 centimeters per second squared. So it's about a 500th of the acceleration due to gravity. The question is, what is theta? You see, when you study, you have to look at these problems and you have to say they could go backwards. We often solve for the acceleration, but instead you could be given the acceleration and have to go backwards. In this case, I say, what is the angle? Well, everything, every single thing we did in this case is exactly the same. This equation still applies to this situation. But mu sub k is 0. So as a result, the acceleration is g times the sine of theta. So if I measure the acceleration, how do I solve this for theta? Somebody tell me, what do I do to solve this for theta? What's the first thing I do? Yeah.
Divide by g.
Divide by g, and divide by g, and I just like to put it the other way. I'll switch things around. And then how do I solve that for theta? How do I get rid of the sine?
Inverse sine.
Inverse sine. I take the inverse sine, not 1 over the sine, but I take the inverse sine or the arc sine of both sides, and I get theta is the sine inverse of A over G. So given that, the sine inverse of the sine inverse of the arc sine of 2.15, I'm sorry, theta is that. 2.15 centimeters per second squared divided by 981 centimeters per second squared. The units cancel. So take your calculators and take 2.15 divided by 981, don't forget to hit equals, and then hit shift sine. I got about 0.13 degrees. Anybody else get that? 0.1255, blah, 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 blah. There is no way that you could use a protractor and a bubble level on that air track and measure that angle. No way. In fact, if I said, what is the angle of the air track, I would have put a glider on it, and this is how I would have calculated it. This is probably the most accurate way to calculate the inclination of the air tract. Just a little over 1/10 of a degree. Very, very small. Look at a protractor and look at 1 degree is and try to imagine 1/10 of that. And it's very, very slight. Yet this allows you to measure it accurately. Quite amazing. Now I think that finishes this chapter. And are there any other homeworks still floating around out there? Are there other homeworks that I assigned? Oh yes, there are, right? There's going up to 23, 24, and 27, right? Are they still, are those the ones that came in? Those are the ones that came in. Okay. I will have to go over those. I'm not going to go over them tomorrow. I'll go over them Friday. I'll have to remember to do that. So let us assign these. And let's see. Wow. Okay. Well, let me assign from chapter 4.
Dr. Love?
Yes. Speak really loud. Yes. Okay, I assigned those. Hallelujah. Okay. All right. And I went up to 42, correct? Okay. Thank you so much. I'm going to assign 3 more to finish out this chapter. 56. 4-56, 62, and 64. All right, 56, 62, and 64. And once again, just to clarify it, if you are in a live session when homework is assigned, it's due the next live session for you. For those of you who are watching on the video, it's due in 1 week. And what I'm doing to avoid total confusion is I'm not going to assign any homework problems in the video tomorrow. So I'm sticking to assigning homework problems on Monday, Wednesday, and Fridays. Otherwise, we will go absolutely bonkers. Okay? Now, on number 64, I will give you a hint. And there's an easy way and a harder way to do it, but the situation is that they give you the coefficient of static friction for a car parked on an icy incline, yes, and they ask you, is it safe to park your car? Well, what they are saying there is that if you have a situation such as this, that as you tilt this, you reach an angle above which it starts to slide. That I call the critical angle. So for the car problem, which is number 64, here's how I suggest you solve it. Assume that it is just ready to slip. In fact, this is the secret for many of these friction problems that involve static friction. In many of the static friction problems, if you consider the case where the object is just ready to break free, in that case, the static frictional force is the maximum frictional force, and you can use that equation. So in the case of the car, if you calculate the critical angle, call it theta sub c, this is the angle at which it just starts to break free. Now, one of the things that they don't seem to tell you is it doesn't say the mass of the car. So what dost thou do? If you're not given the mass of the car, what do? You either find it, or maybe you don't need it, but you assign a variable and you plunge forward. Okay? What you will find out is it will cancel out. If you're clever, you'll see the equations, it will cancel out. Once you know the critical angle, well, obviously, if it's parked on a slope less than that, it's safe. And if it's on a park more than that, it's not safe. You just do one problem, and then you say, they give you a 12, a 9, and a 6-degree angle. So if any of them are above the critical angle, then it's going to slip, and I wouldn't do it. By the way, my sister-in-law's car didn't slip off of a slope, but it slipped out of gear, rolled right down her driveway, out into a 4-lane highway, and into the front of a fully loaded dump truck. That was the end, and she watched it go down. I mean, it's almost laughable. If it was my car, I wouldn't be laughing, but it's like, you know, what do you tell the insurance company? Well, you know.
Mechanical failure.
Well, these things happen, you know. Farmers insurance, this kind of stuff does happen. It was total. Boom, just, that was it. Okay, but to see it, to watch your car, you know. Oh, well. So take that into account, all right? All right, so that finishes that chapter, and we're coming back to chapter 5, so don't worry about chapter 5 and 7 and all. We will come back to them, but I want to make the jump to chapter 9, and to do that, though, we need to consider the concept of torque, and torque is actually done in section 8-5. So I'm making a jump, well actually 8-4. 8-4. Because we're going to need it. If you're into hot rodding or performance automobiles, you will hear about torque. Right? Because we're going to need this in the beginnings of chapter 9, where we talk about statics, where we think about a bridge sitting there, or a classic thing is if your arm is being held up by the tendon here, and it's in a static situation, we want to find the force in the tendon and all this kind of thing, or where is it attached, and so on and so forth. But to get there, we need to talk a little bit about torque. What's going to happen here is, up until this time, we have ignored the shape of any of the objects that we have been dealing with. We've ignored it completely. We've just drawn a dot for a skier. We just had a skier coming down an incline. We might have drawn a square box or whatever, but when we drew the free body diagram, we just draw a dot. We can't do that anymore. What happens with torque is the place where the force is applied makes a difference. We now have to take into account where the force is applied to the object. It's going to make a difference. So our free body diagrams are going to have to expand a little bit to crudely show the shape of the object, okay? So we're going to have to ramp up our free body diagrams a little bit. Now, we're all familiar, I hope, with this. Or in magnitude form, that. Now, what this is saying is that a net force, and I'll put the word net here just to remind us, though we often omit it. If you ask, what is a net force? The answer is whatever it is in nature that alters the velocity of an object. That is what a net force is. Whatever changes the velocity of an object. Now, you can do a basic experiment. Boy, these things are handy. I can zoom out to include the table, but then you can't see the board very well. So, here's an object sitting on the surface. And I want you to watch. If I apply a force to this just right here and push it, it translates. It goes that way, right? Everybody see that? What's going to happen if I apply the force this way? It rotates. Rotates. I can't do it here. Or if I apply it here, it rotates. Like that. Same force, it wants to rotate. And it moves. Whoops. So there's a combination where if I apply the force just properly, this will just translate. This is a translation. This is a translation. This is a translation. But if it does this, this, or this, or this, is a rotation. Likewise, I can even do it. If I apply the force here, it will translate. But if I apply the force here, what will it do? Rotate. The point of application of the force affects the rotation. Can anybody sense, regardless of where I apply the force, can you guess how I must apply the force such that it doesn't rotate? Now, if I do it just right here, let me see if I can do this. See? See that? But if I point it straight, it turns. If I point it straight this way, it turns. But if I angle it at just the right angle, it translates. It goes like that. How must I apply the force such that it doesn't rotate? Anybody see it? Yes?
I want to say equally to both back and side.
I'm only applying one force, so equality doesn't. I'm only applying one force. You see, okay, let's look at it this way. Let's introduce it. When I apply the force, let us introduce the line of action, the LOA. If this is a body and I apply a force to it at this point, so here's my force F. If I draw a line through the point of application, this point right here, by the way, is called the POA, or the point of application. Because clearly, whether it rotates depends on two things. Where I apply the force and the direction I apply the force. Both of those come in. So the line of action is a line through the point of application parallel to the force. There's the point of application. Here's the force. So this, well, is, and it goes in front of and behind it. So, thinking in terms of the force where does the line of of action have to go such that it doesn't turn?
To the center.
Yes. And in fact, when you say center, what do you actually mean?
I mean, like,
Halfway down, halfway in, because if this were in space, imagine we were in 0G. I'd be barking if we were in 0G. 0G is not fun. 0G is not fun. 0G feels like you're falling on one of those rides and it never stops.
that's fun.
Yeah, no, it's not. You throw up. Astronauts throw up. Now you get used to it. But if I push on this, what would happen if I pushed on it up here? It would do that. If I did it here. But if the line, no matter where I push on it, this thing has, we're going to talk about this, a center of gravity or a center of mass. And it is halfway down, halfway over, and halfway this way. The center is inside of it. If the line of action goes through that center of mass, it won't rotate when I apply the force to it. It'll translate, but it won't rotate. Or if it's already rotating, it could be spinning already, okay? Its spinning won't change. In fact, the best way to think about what a torque is that forces cause velocities to change, torques cause rotation to change. A torque is that thing in nature which causes the rotational velocity of the object to change. This is a translational velocity. This is a rotational velocity. Okay? If I translate this, this has no rotation. But if I throw it from the end, now it rotates while it goes. What we are going to do, later on down the line, is consider fully rotation. It's a big part of this course. But right now, when we get to the statics problems, we want to consider the situation where the rotation doesn't exist, where it doesn't rotate. You see, a bridge that is sitting there, not only is it sitting there, but it's not rotating. I could spin this thing, and it could, if we were in no gravity, it would spin here, but have no translational motion. Objects can have rotational motion, they can have translational motion, or if I threw it, they can have both. When we get into chapter 9 where we do statics, not only are they not moving, but they are not rotating. So we have to understand what is the situation that exists when it doesn't rotate. So, we introduce the line of action, the LOA. And we introduce the point of application. Now, you'll start to get an idea for this. Suppose this is a piece of metal. An irregular piece. Now we're just going to do sheet metal for the moment. We'll start with flat objects that aren't three-dimensional. That's a piece of weird-ass shaped piece of metal. Okay? And I drive a nail into it right here. There's a nail. Bam, 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 bam. So it can do this around the nail. That is called the pivot. Okay, now use your instinct. If I apply the force like that, and let's assume that it's sitting still, will it start to rotate if I apply a force at that point in that direction?
Yes.
Yes, it will. Which way will it rotate? Counterclockwise. That's important. Torques have a sign. Counterclockwise and clockwise. Generally, counterclockwise is considered positive because the mathematicians measure angles this way as being positive. So this is a positive torque. What if I were to change that force, change the direction of that force, so that the line of action went through the pivot, would it rotate? No, no. What if I were to do that? Yes. Would it rotate the same way? Nope, it's going to go clockwise. Okay? So you see that the effect on rotation of a force depends on where it is applied and where the line of action goes. Okay? And if we actually quantify it, and that's what we're going to get to today, we've got just enough time here. So read this section. If we apply a force, I'll apply it here. And this is the line of action. Okay? And here's the pivot. By the way, since I'm on this, would the torque change if I left the force and direction it's applied exactly the same, but I move the pivot? Sure. Right now, which way is it going to rotate? Counterclockwise. What if I move the pivot right along the line of action? No. No. So the torque depends on where the pivot is, it depends on the line of action of the force, and it depends on how strong the force is too. Obviously, if I increase the force, I increase the torque. It can be all simplified by saying the following. If I draw the line of action and find the perpendicular distance from the line of action to the pivot, and we call that perpendicular distance D. Okay? The magnitude of the torque, and this is a tau. This is a T. A tau has a curly hat. This is tau. Okay? This is pronounced tau. The magnitude of the torque is the magnitude of the force times the distance of closest approach to the pivot of the line of action. So if it goes right through the line of action, or if it goes right through, if the line of action goes right through the pivot, what's D? 0. And what's the torque? 0. Now, and generally, we also say, you have to, again, this is by inspection. You have to make a diagram and look at it and decide, is it going to go this way or this way? Generally, counterclockwise is defined as positive, and clockwise is defined as negative. Typically, we draw it like that. That direction is positive. Some people can't keep clockwise and counterclockwise correct. Okay, you ever seen a left-handed clock? Do we have any lefties here? You're the only lefty? All right. We'll have to go out when all this is over and celebrate, okay? Yeah, all right. Lefties, all right? Counterclockwise is plus and clockwise is minus. So we usually use this. Now, we've got just enough time. What would the units be? What are the units of force? Newtons. And the units of distance? Meters. So the units of torque are Newton meters. Now, unfortunately, in chapter 6, when we talk about energy, it turns out energy, which is a totally different thing, also has units of Newton meters. The joule is a Newton meter. Whenever you use the word joule, though, you're implying that you're talking about energy. If you're talking about torque, you can use Newton meters. Either way, it's going to work out the same. But some books, like this one, say this is a meter Newton to kind of distinguish it from a Newton meter, though technically, mathematically, they are the same. If you see meter newtons, they're trying to say that it's torque they're talking about. If you see newton meters, it's an energy problem. So this is one point of it. Turns out that in nature, there are quantities that have the same units, but are absolutely physically completely different things. So you must be very, very careful. Yes, Autumn?
It's time.
It's time. Thank you. All right. So, let's stop things.